I won't be lecturing Monday because I take the day off for Yom Kippur. Peter has agreed to sacrifice his position in the Book of Life and stand in for me, for those of you attending. And the assignment is to read section 3.4 and these homework assignments. Also, those of you who participated last year will know the Putnam competition is a fun competition which is given nationally to math students. We've usually done pretty well in the standard Harvard way of not studying for the exam but acing it. And it's given Saturday, December 6th. If you want to sign up on the 5th floor bulletin board opposite Professor Taubes' office. And even if you're not going to take it, sign up, because it's very important that we get enough exams. We always get a couple of walk-ins that day. And if we have enough exams, they can take it. And if we don't, they can't. Okay, so last time we defined what a field was. And we had various examples like the real numbers and the finite field, the integers mod p. And then we had the notion of V, a vector space over F, which was an abelian group together with a scalar multiplication law from F. And we defined the notion of a linear map, homomorphism of F vector spaces. So today we're going to investigate vector spaces in more detail and do the notion of span and basis. Now, many of you have seen this for real vector spaces, and the key thing is that it works perfectly well for vector spaces over an arbitrary field, and it can't hurt to review it because it's so important. So if we have a finite set, V1, so in all this lecture, I'm going to start with the hypothesis that I have a vector space over a fixed field F. And I take an ordered set of vectors, which means it matters which one goes first and which one comes last. So that'll be an ordered set of vectors in V, ordered finite set. And if I want to forget the order and I just remember the set, I'll call the set S, which is the collection V1 through Vn, where I forget the order. So that's just the set. Okay, so you say that a linear combination of these vectors is just is any vector that you can express as a scalar times V1 plus a scalar times V2 plus a scalar times Vn. So where the AIs are elements of your field F. So AI times V is the operation of the scalar times the vector, and then you add it to this and this and this. So it's all the vectors you can get by combinations of the fixed vectors in the ordered set. And the collection of all linear combinations is called the span. And the span only depends on the set S, because addition is commutative, so it doesn't really make any difference how you order the set of vectors. You'd get the same vectors W in the span. And let's call that W. And the proposition or the observation is this is a subspace of V, closed under addition and scalar multiplication. Well, if you have two vectors of this form and you add them, you clearly get another vector of the form. So if you have a W prime, let's just check that. W prime is V1, V1 plus Bn, Vn. And if you use the associative law or the distributive law of addition, you find that W plus W prime is A1 plus B1 times V1 plus An plus Bn times Vn. And you find that a scalar times W is CA1 times V1 plus CAN times Vn. And since the field is closed under addition and multiplication, these vectors are of the same form as the original one. They're linear combinations of the VI. And so you have a subset of V that's closed under addition and scalar multiplication. It's a subspace. That's called the span of those vectors. All right, now we say that V is finite dimensional Oh, by the way, we'll decide convention, and you have to be careful about this because it'll come up in induction arguments. If S is the empty set, which is certainly a perfectly good set of vectors, and the ordered set would just be the empty set, then we agree that the span of S is the 0 subspace in V. So the span of any set of vectors, whether it's empty or not, contains the 0 vector. Otherwise, it wouldn't be a subspace. Otherwise, we'd have problems with the empty set. So that's just a convention. OK. And we say V is finite dimensional if there is a finite set S of vectors in V that with the span of S equal to the entire space, so that you can get any vector as a linear combination of a finite number of them. So an example of a finite dimensional vector space versus a non-finite dimensional vector space. So example, V equals Fn is finite dimensional if you take the vector v1 to be the vector 1, 0, 0, and v2 to be the vector 0, 1, 0, 0, and finally vn to be the vector 0, 0, 1, then the vector a1, a2, an, and that's a general element of this vector space, which is just n tuples of elements in F, is the sum of the ai times the vi. I equal 1 to n. That's more or less obvious. So those vectors, these n vectors, span this vector space. So that's finite dimensional. A non-finite dimensional vector space, or we might say infinite dimensional vector space, non-example, is the polynomials in X with coefficients in F. There is no way that you can get any polynomial as a linear combination of a finite number of them. Because if you have a finite set of polynomials, one of them has the largest degree. And if you take any linear combination of polynomials of degree less than or equal to n, you get a polynomial of degree less than or equal to n. But they're polynomials of bigger degree. So this is not finite dimensional. And the argument is use the degree of a polynomial in X to show that you couldn't get it as a linear combination of a finite number of them. So from now on in this talk, and really in this chapter, we're only going to talk about finite dimensional vector spaces. Infinite dimensional vector space is a very interesting subject. It's more a subject in analysis than algebra. When people realized at the beginning of the 20th century that a lot of results in physics could be formulated in the language of infinite dimensional vector spaces, they became fascinated with them. But we're going to get the theory of finite dimensional vector spaces down today. So from now on, we're going to make the assumption that there's a finite set that spans our vector space. Okay? So that's the notion of span and finite dimensionality. Now the second notion is the notion of linear independence. Which is expressed as follows. You say a set of vectors v1, vn is linearly independent if the relation a1, v1 plus a2, v2 plus an, vn equals the 0 vector only holds when a1 is equal to a2 is equal to an are all the 0 scalar. Of course, if you take any combination of vectors and you take 0 times v1 plus 0 times v2 plus 0 times vn, you get the 0 vector, because 0 times anything is the 0 vector, and any sum of 0 vectors is the 0 vector. If that's the only way you can get a linear combination of them, to be 0, then you say the vectors are linearly independent. Clear? You've seen this notation before? Okay. So the whole tension in vector spaces is between things that are linearly independent and things which span. So let's do a little bit more complicated example. Let's take the space R3. And let's take the following collection of vectors. Let's take V1 equal 1, 0, 0. V2 equals 1, 1, 0. And V3 equals 1, 2, 3. Okay. What is the span of the set V1, V2? Well, I claim that's all things of the form, all vectors of the form V equals A, B, 0. Because if I want to hit this, if I want to get this vector, it would be B times this vector plus B minus A times that vector. Right? Because I'd already had B in the first place. I'm sorry, A minus B. Is that right? Let's see if I want to get A here. Sorry, A minus B. There we go. But I could never get any coordinate in the third place because both V1 and V2 have 0 in the third place. So any multiple of V1 does plus any multiple of V2. So the span is that subspace. And I also claim that V1, V2, and V3 are linearly independent. Are linearly independent. Because suppose I had some relation between them. A1, V1 plus A2, V2 plus A3, V3 equals 0. Well, if you write down what this vector looks like, in the third place it has 3A3. So 3A3 had to be equal to 0 because the coordinate of the third place of these two vectors is both 0. So if 3A3 is equal to 0, and we're in a field, so we can divide by 3. Whoops. Oh, this is R3. Good. So 1/3 exists. That means that A3 is equal to 0. Since A3 is equal to 0, it's a combination of V1 and V2. Now, I claim that the second coordinate of this vector is A2, because you get no second coordinate in V1. So that means that A2 is equal to 0. And if A2 is equal to 0, it's a multiple of V1. And the only multiple of V1, which is the 0 vector, is the 0 multiple of V1. And so we see that the only way you can have a linear combination which is 0 is if all the coefficients are 0. Okay? You're probably used to doing exercises of this nature. Okay? Next. Sure.
I noticed that you put the V1, V2, V3 are linearly independent. You wrote the order. You made the order significant.
In fact, it's not significant. It's just a question of the set. Because, again, if you had a linear relation like this, you'd get a linear relation if you reordered the V's.
I thought so. I just didn't know about the notation.
You're absolutely right. Thank you. The set is linearly independent. Okay, we say an ordered set, and this is important to have it ordered. V1 up to Vn is a basis of V if it spans V and is linearly independent. So you need both conditions. You have to write every vector as a combination of these. That's the span. And if you had a combination that's 0, all the coefficients are 0. What this means sometimes it's nice to have a definition and to actually know what the definition means. What it means is that every vector W in V is uniquely expressed as a linear combination W A1 V1 plus plus an vn. The span means you can write it as a combination, but the linear independence then says that that combination is unique, because suppose it were written in another way. Suppose it were written as b1 v1 plus bn vn, another way of writing it. And take this vector minus this vector. Okay, that's w minus w, so it's the 0 vector. On the other hand, it's then 0 vector would be a1 minus b1 times v1 plus an minus bn times vn. And by linear independence, that says that all the coefficients have to be 0. So this coefficient is 0, and this coefficient is 0. In other words, a1 has to be equal to b1, a2 has to be equal to b2. And so, consequently, we didn't have really a new expression at all. And this expression was unique. That's the beautiful thing about a basis. You can not only express it as a combination, but that combination is unique. In fact, for example, this forms a basis of R3. We checked that they were linear independent. You also have to check that they span. Well, we checked that the first two spanned a rather large subspace, and you can see that this third one actually ends up spanning the entire space. Okay, now, what is a basis in terms of the in terms of our fancy language? Because you've seen this definition of a basis undoubtedly before. In terms of the language we used last time, a basis gives rise to an isomorphism of vector spaces from V to the vector space f to the n, which takes an arbitrary vector w in V to its coordinates in this unique expansion of w with respect to the vectors v1 through vn. Okay? Good? Now, that is a homomorphism, because if you add two vectors in V, you add the components of v1, v2, v3, so you're adding a1 to b1. Suppose we had another vector. So now we're going to call this vector w prime. If we add w to w prime in V, we get a1 plus b1 v1, an plus bn vn. And so when we apply f to w plus w prime, we get a1 plus b1, if you just take the definition of s that I've given here, an plus bn, which is exactly f of w plus f of w prime, right? Because this is the addition law in this vector space. Likewise, if we apply f to a constant times w, well, if you multiply w by a scalar, you multiply all the coefficients of the v's by that scalar. So you get ca1, ca2, can, which is nothing but c times f of w, because this is scalar multiplication in this vector space. Now, moreover, I claim so that shows that it's a homomorphism of vector spaces. I claim it's an isomorphism. First of all, it's onto, because if you give me any n tuple here of scalars, I can make this vector w and v, I can take my vi and multiply them by those specific scalars and add them up. That gives me a vector in v such that f of v is equal to your set of scalars here. That's the onto. And it's one-to-one. Well, we just have to check, because it's a homomorphism of groups, that its kernel is trivial. Well, if f of w is the 0 vector, that means all the a's are 0, which meant that w itself was the 0 vector. Okay? So, isomorphism of vector spaces. Conversely, we're going to see that to every isomorphism of vector spaces of this sort, we get a basis of V. It's really one-to-one correspondence between a basis and such isomorphisms, identifying our vector space with this vector space. I haven't done that yet. It's just something in the future. So here's, since I just mentioned in the future, consider the following. People say you can't see the future, okay? But I'm going to disagree with that. You can't see your own future. You can see other people's future. It's a very interesting time question. So here's an example of how you can see other people's future. You're driving down the highway, right? And on the other side of the road, you see a backup for like 5 miles. And you want to see the people who are driving into the backup, you want to say to them, add an hour to your trip. You've just seen their future. They can't see it, but you've just seen their future. True? Okay. Okay. All right, let's prove a couple of nice theorems. So we're going to go 2 ways. What was so funny? That was just a side comment. I can see your future in this course. Okay, so if S, pardon? Well, I can't, you can't see your future, so I can't tell you your future, right? That would violate the fabric of time. What do they say? They always do that in Back to the Future. Oh my God, we've rent the fabric of time. All right, let S be a set that spans V. We know there is such finite set because we've assumed V is finite dimensional. Okay. Then a subset of S gives a basis for V. So anytime you have a set that spans the vector space, you can maybe it'll be a basis itself, but if not, some subset of it will be a basis. Okay. So, proof, if the elements of S are linearly independent, we are done. Because that's the second condition you need on S to be a basis. So if not, we have a relation A1 V1 plus AN Vn. The elements in S are V1 through, I should have said that. We have a relation equal to 0 with some AI not equal to 0. So either they're linearly independent or there's some linear relation between them. And some linear relation would mean some linear combination where one of the coefficients is non-zero. So you get it. So since the set wasn't particularly ordered, I now order the set so that we can assume, can reorder so that, for example, A sub n is not equal to 0. Namely, so that this last coefficient is non-zero. Why not? Okay. Take this over to the other side. Then AN Bn is equal to minus A1 V1 plus AN minus 1 Vn minus 1 in V. That's what that linear relation means. And now, and this is the key point, we use the fact that we're in a field. And when you have a non-zero element in the field, you can write down its multiplicative inverse. This is the only thing we're using about fields. Okay, so AN inverse exists. That's, if you look at all the linear algebra you did over R and C, this is the only thing you're really using about it. You're not using the fact that you have convergent Cauchy sequences in the reals or anything like that. You're just using that if a non-zero element has an inverse. So AN minus inverse exists. Multiplied by AN minus 1, you get Vn is equal to minus 1 over AN times A1 V1 plus AN minus 1 Vn minus 1. Which says that this vector is in the span of the previous ones. So that anything that you could write, that you wrote using the first n things, you could have already written in terms of the first n minus 1 because you could replace any multiple of Vn in your expression by the corresponding multiple of this combination. So hence, the span of S is the same as the span of the set v1 through vn minus 1. And this we assumed was v, because we said that S spanned v. So we've shown that if the set was linearly dependent, we'd be able to throw a vector out of it and get the same span. And now we have a smaller set that spans v. So maybe it's linearly independent. If this set is linearly independent, this set meaning this set, we're done. If not, repeat. To find another linear relation and throw another vector out of the set, and we get down to a smaller set. And since we started with a finite set, we can't repeat this process indefinitely. We eventually get down to a set which is either linearly independent of basis, or we keep throwing out vectors to the point where we get down to the zero set, the empty set. Right? The empty set is a basis for its zero vector space. Okay? So we're done. Repeat until done. And so by throwing out things one at a time, every time we get a linear relation, until we don't get any more linear relations, we get to a point where we get a basis. Okay? Let's go the other way. Now we're not going to start off with a spanning set. We're going to start off with something which is linearly independent. So spanning set should go down, linear independence should go up. So here's another theorem. If L is S is span, L is linearly independent set of vectors, it can be extended to form a basis of V. Namely, you can add vectors to it one by one to get a basis. Okay. Okay, so a proof. If L spans V, then we're done, because it's a basis. If not, let S be a finite set spanning V. Since V is finite dimensional, there is some finite set that spans it. And let V be an element in S which is not in the span of L. Now there has to be such a vector in S which is not in the span of L. And the reason is that if everything in S were written as a linear combination of things in L, and everything in V can be written as a linear combination of things in S, we would have written everything in V as a linear combination of things in L. But L didn't span V. So there has to be some vector in S which is not in the span of L. Then we claim that if we take the union of L and V, call that maybe L prime, is linearly independent. So that if you add V to L, so we just add one vector to L, we get something which is linearly independent. Here we threw one vector out of the spanning set. So let's see why that's true. Why? Suppose that L were the vectors W1 through Wm. And suppose we had a linear relation between the vectors in L and V. And suppose, and the sum of AI Wi plus BV is equal to 0. That would be our linear relation. Okay. Now I'm going to claim that all the coefficients are 0. Well, let's first see that B has to be 0. Or else, by the trick we did last time, V is equal to minus 1 over B, the summation of AI Wi, is in the span of L. Again, we're using the fact that in a field, anything which is non-zero is invertible. Okay? So this coefficient has to be 0. Hence, the summation of ai wi is equal to 0. Because we didn't need b in this linear relation. But that implies that all ai are 0 as L was assumed to be linearly independent. Okay? So anytime we had a linear relation, we've just proved that all the coefficients are 0. So that means that this is a linearly independent set. Now, the next thing we ask is, if L prime spans, we are done. If not, there is a vector v prime in S, not in the span of L prime, by the same argument that we did before. And then if you adjoin that to L prime, you get a linearly independent set. And you keep adjoining vectors in this finite set to L, as long as it doesn't span V. You keep adjoining vectors, you keep getting linearly independent sets. Well, you can only do that a finite number of times because S is a finite set. So ultimately, you either adjoined everything in S, and you certainly span because S spans, or you've gotten to the point where your finite set by adjoining some of these vectors actually spans, and you have a basis. Okay? Good. Okay, cutting the basis down. Now here's the key proposition, which is the one thing that's slightly non-trivial in this lecture, and the only thing where you don't want to bury yourself in notation with. All right, here we go. Theorem, main theorem. If S, which is V1 through Vn, spans V, and L, which is W1 through Wm, this is an M, is linearly independent, then you can't say anything about this vectors and these vectors. They're just completely different vectors. But only thing you can conclude is that the number of vectors in the spanning set is at least as large as the number of vectors in the linearly independent set. That's what we're going to prove. So spanning sets are bigger than or equal to linearly independent sets. Okay, so let's prove this. Proof. Since S spans, we may write every element in W, which I'll call Wj, as a combination, linear combination of the elements in V. So I'll write that as A, Ij, Vi, where I sum from I equal 1 to n. Okay. So I write my question. Yeah.
Let's assume that all the elements of W are in the same vector.
Sorry. This is linear independent in V. Everything is in the same vector space, but they're just different sets of vectors. So I have one set with n elements that spans, another set with m elements that's linearly independent. I'm going to show that whatever those sets are, the number of elements in the first is at least as large as the number of elements in the second. So I write every element in the second, which is an element in V, in terms of the spanning set, like this. Okay? Now, suppose I want to make a linear relation on the W. Try to make a non-trivial linear relation on the W, the Wj. So in other words, I'd write 0 in V as a combination of Cj, Wj, j equal 1 to m. We're not supposed to be able to do that unless all the c's are 0, right? That's the hypothesis that the W are linearly independent. But let's see if we can see what such a linear relation would mean. Well, now I replace Wj by that sum over there. So that's the sum from j equal 1 to m, Cj, times the sum from I equal 1 to n of Aij times Vi. In other words, I take this relation that I'm going to make on the w's, and I turn it into a linear relation on the vi's. In other words, it becomes the sum, and I'm going to change the order of summation between I and j. Oh my God. Oh my God. I changed my notation here in the middle, so you see, we'll see if we can actually do this. It becomes I equal 1 to n of the summation over j equal 1 to m aij times cj times vi. Okay? Okay. Now, if we can arrange that we're trying to look for this linear relation. So we're trying to look for a vector c1 up to cm, which is not equal to the 0 vector. Now, one way we could get this relation, this could be 0, is if all these coefficients were 0. So if we can make, so here's the argument. If we can arrange that the summation over j, aij cj is equal to 0 for all I, then this vector is certainly the 0 vector because the coefficients of vi are these sums. So we could certainly get this equal to 0 if we could arrange this. If we could arrange this with sum cj not equal to 0, then the wj could not be linearly independent. Now, can we arrange that? Well, let's think of what this is. The i's go from 1 to n. So this is n equations. And we're trying to solve for the cj, so that would be m unknowns. They're actually linear equations. And it's a general theory in linear equations, which you all know, and I'll just sketch out for you briefly, that if you have more unknowns than equations, you can always find a non-trivial solution. So if m were bigger than n, more unknowns cj than the I equations, we can find a non-trivial solution. Namely, we can find a solution to this system of equations with some of the cj's non-zero. But that would be a problem for us. This would imply that this sum was the 0 vector, and it would be a combination with non-trivial coefficients of the wj, which would contradict our hypothesis that the set L was linearly independent. So if m is bigger than n, we get a contradiction to these two hypotheses. And consequently, these two hypotheses imply that n has to be bigger than or equal to m. Now, let's review this. When you have linear equations and you have more unknowns than equations, you can find a non-trivial solution. How does that work? Well, this is the sort of thing one learns in 8th grade. I mean, if you start with one equation and two unknowns, like 2x plus 3y equals 0, you can find a non-zero solution, x and y. And likewise, if you started with two equations, plus 4z is equal to 0, and 2x plus 7y plus 8z equals 0. If you had two equations and three unknowns, then you could also find a non-trivial solution. You just eliminate one of the variables by subtracting one of the equations from the other. Then you get one equation and two unknowns, and we know how to solve one equation and two unknowns. And likewise, when you start off with a system of linear equations, you keep eliminating one equation and one unknown, and eventually you get down to a system where if you have more unknowns than equations, you have 0 equations and a certain number of unknowns. You just set the unknowns equal to anything you want and go back. So this is the process of elimination theory, which you study in 9th grade algebra in the context of 2 equations or 3 equations. Of course, it becomes a very interesting question when you have exactly as many equations as unknowns. That's totally interesting. But when you have more unknowns than equations, you have freedom in linear equations always to choose a non-zero solution. So if you want to review this, this is reviewed in Chapter 1. Where he shows you how you actually find the non-trivial solution. And this is kind of one of these theorems where it's best to write out the proof yourself so you understand the notation and what you're actually doing here. But the system of equations is determined by this coefficient system Aij that we got here. They give you the coefficients of the equation. And the equations you're really solving are things like this. If I wrote the equation like this, and you were trying to solve for the xj, calling them cj, so you had a certain number of equations, you had more unknowns in the equations, you'd be able to find a solution, Cj. That would give you this non-trivial dependence on the Wj. Okay, this is the big theorem, because this allows us to say the following. Let me make a corollary of this. All bases of V have the same number of elements. And that number of elements is by definition called the dimension of V. So it's an integer that is the number of elements in a basis. That's the first statement. The second statement is all spanning sets have more, the number of elements in S, at least the dimension of V. All linearly independent sets have the number of elements in the linearly independent set less than or equal to the dimension of V. So 2 and 3 follow from 1, because we saw that if the theorem we had on spanning sets is if we had a spanning set, we could always reduce it to get a basis. Right? So the number of elements in it has to be at least the number of elements in a basis. And this thing follows from our theorem on linear independent sets, because we saw in a linear independent set, we could always increase it to get a basis. So the number of elements in it has to be less than or equal to the number of elements in a basis.
Is the dimension of the zeros, of the empty set, or I'm sorry, the zero empty set?
Thank you. The dimension of this is equal to 0. The dimension of the space f to the n turns out to be n. So there's a vector space of any positive dimension. This dimension is supposed to be a non-negative integer. Good question. Okay? So we now have got a vector space of any given dimension. We're going to have to prove this, but it's not hard, because you just have to write down a linear independent spanning set. And the proof of this is use the standard basis. Where Vi is the vector which has just a 1 in the ith place. It's easy to show that spans and it's linearly independent, so that shows the dimension of this space is n, as you might expect. Okay, let's prove the corollary. Well, a basis is a set that's linearly independent and spans, so let's let the first basis B be the first basis, and the second basis be B prime. And since B spans and B prime is linearly independent, we know that the number of elements in B is at least the number of elements in B prime by the main theorem. And since B prime spans and B is linearly independent, we know the number of elements in B prime is at least the number of elements in B. And if you have two integers and they're both greater than or equal to each other, they have to be equal. Okay? Okay. And let me give you one more amazing. So bases are the key to analyzing vector spaces. We're going to see that a vector space itself is beautiful and symmetric and et cetera, but if you really want to get down to the nitty-gritty, you usually choose a basis. And I'll give you one more very cool thing about bases. So suppose W is a subspace of V. They're all finite dimensional. And W1 through Wm is a basis for W. Then we may extend to a basis for V. Namely, what I mean by that is you take the first elements of your basis to be W1 through Wm, and then you add some new things, Vm plus 1, Vm plus 2. You can adjoin elements to that set so that you eventually get to a set which is a basis for V. You can use your original basis for W and just keep pushing it out to get a basis for V. Why is that? Because the original set was linearly independent and spanned W. Well, if it's linearly independent, it's linearly independent in V. If no linear combination is the 0 vector, but the 0 linear combination, that's also true in V. You don't have any more linear combinations of this thing in V than you did in W. So that this is a linearly independent set is linearly independent in V. And we saw that you can always take a linearly independent set and extend it to a basis. So there it is. Right? That was one of our propositions on linearly independent sets. Now that makes the structure of quotient groups, et cetera, in this situation extremely transparent. Because remember that when we had a subspace, and this is much nicer than the theory of arbitrary groups. And when we had a subspace, W, we had a quotient space gives a map V to the cosets of W. Now in that map, the first m vectors go to 0 because they're in the kernel. Right? So gives a homomorphism, F. So in fact, I don't know if Peter assigned this to you for homework, the F of the Vn plus 1, Vm plus 1, comma F of Vn, that's ordered set of vectors, gives a basis for V mod W. And consequently, the dimension of V is the dimension of W plus the dimension of V mod W. Because n is the dimension of V, and we needed m vectors to give a basis of W, and I claim the rest of these things give a basis for V mod W. Got to find that. Now notice what's going on here. We've really got a subspace of V that's mapping to V mod W. So if we let W prime be the span of Vn plus 1 up to Vm plus 1 up to Vn is a subspace of V mapping isomorphically to V mod W. So in some sense, this isn't just a quotient. It's just not a homomorphism image of V. You can think of it as inside of V. Now, that you can't do for groups. Don't ever think you can do that for groups. If you take the group Z mod 2, Z mod 4, that's a perfectly nice group, G. And it has a very nice subgroup, which is called H, which you could write as 2z mod 4z, which is isomorphic to z mod 2z, the even things mod 4. So this is a cyclic group of order 4. It contains a cyclic group of order 2. The quotient group is cyclic of order 2, because it has to be of order 2, and any group of order 2 is cyclic. There is no other cyclic group of order 2 except for H in here. So you cannot find another cyclic group of order 2. There does not exist an H prime in G mapping isomorphically to G mod H. Because H prime would have to be of order 2. But the only subgroup of order 2 is H. And if you take the image of H in the map to G mod H, it's 0. So this is a remarkable fact of vector spaces, that because of the existence of bases, you can find a subspace that in some sense lifts this. Don't think you can do that for a general homomorphism. I've just warned you. Okay, we'll put a little Bourbaki sign next to it. Roulette. Okay, have a good weekend. Peter will see you Monday.